so far, I don't think I'm too far off, but this is almost state of the art. Okay. There are a few ways, and I would just want to add this DLIT facial landmark detector in addition. There are a few ways called OpenFace, FaceNet. One of these, I think, is OpenFace. No, one of them is one of them is used by Google. This FaceNet, which actually modified how the other algorithm is done. Okay, and this is the whole process of OpenFace. As you can see, this is the input image. The face is detected. Okay, and this is the bounding box. What they call the bounding box is actually a technical term in face recognition or any computer vision context. Then somehow or other it identifies those parts of the face where it wants to call as a feature. Further, then once it detects, okay, then it transforms this face into a vector. Okay, actually this isn't really here. This is and then once okay, sorry about that. As you can see, it detects a face. I don't know what it's transforming this for. It could be face alignment, face alignment, because sometimes the face is crooked, so they got to change it to make it straight up again. Face alignment, and then after that they crop the whole picture. Okay, and this is the only thing that actually goes into the database, this guy's face. Okay, and inside the database, this face is processed through a neural network. And what it does is this neural network converts into 128 degree dimension, 128 dimension, which basically means 128 bit vector or 128 bit, 128 number vector. Then a vector with 120, a vector or matrix with 128 numbers only. Okay, and then once you have the 128 dimension vector to represent Sylvester Stallone's face, you can send it for either clustering, similarity detection, which is figuring out the location, figuring out the distance, or classification. These are all ways and means by which to recognize the face. So implicitly that there is a database down here of faces with names that this query, 128 dimension query, can be compared against. Okay, I'm gonna take a break here. Anybody got any questions? This is OpenFace algorithm. This can get quite complicated already. But strangely enough, the OpenCV, again, a lot of this is hidden by OpenCV. So the OpenCV, you only need to do the calling. You just call the procedure, that's it. Okay, the next one is something called, the next way of expressing the face is called the FaceNet. FaceNet is a bit different. Remember, the overall purpose of this is to get a query vector and then to compare that query vector against the reference database. Now, what is in the reference date? Then after that, what you can do is you can actually, the one that's closest to the query vector is taken as the match from the reference database. FaceNet changes the requirement a bit. FaceNet actually maximizes maximizes the sum, or maximizes the probability that that your query will be similar to these guys, okay, these guys, but minimizes the probability that your query will be dissimilar from these guys. So you can see that there is a tree branch what we call a Siamese twin network here. Okay, there are actually 3 CNNs here. And this CNN, there's another CNN here that calculates the what they call a triplet loss. And once this triplet loss is maximized in the database, then it's far more accurate if you compare a query vector here. Now, this is pretty complicated, but it's not, to go into depth, it's even worse. So please forgive me if this is a bit confusing or doesn't convey sufficient information, but please feel free to ask questions, and if I can answer them, and I'm not saying that I can answer them because this is already going pretty deep already.
Okay, Daniel, how accurate can they detect twins? You know, identical twins. Can there be any error?
I would. No, that's interesting. I would say that, yeah, it's difficult, okay? I would say that there is a good enough possibility that the twins can be mistaken for each other, okay? But you see, basically, this can only do what is given to it. If you give the algorithm sufficient photos or sufficient information to tell between the twins, then it's very possible. But if you don't give it sufficient information, then of course it will not be able to tell, it will not be able to tell. So the key thing is that this algorithm or this new generation of algorithms, they can recognize a face up to 99.95 or some even 99.98% certainty. Okay, but that all depends if your database is sufficiently large enough and well-defined enough to distinguish that. You cannot give it bad data, train it on bad data, and then expect it to do well. Okay, so if you have twins, then one twin actually has certain differences which are quite visible. Then yeah, it can distinguish the face just like any other face. But again, that is if there are visible differences. If there are no visible differences, then I would say it's not really, it won't be possible.
But the way I see it, the banks are having great confidence in this face recognition, because now you can enter, using the apps. You can easily go into the bank's. You can log into your account. They have that way. I think they have great confidence in face recognition.
That depends. Again, I say if you give the algorithm sufficient information to make the distinction, fine. Okay, but if you don't give the algorithm sufficient data, it cannot come out with the data itself. Okay, the process of training a CNN or any combination of CNNs for recognition is that somehow or other it finds a point where it can distinguish, it can say that this face belongs to this face. So it depends on the reference data. If the reference data cannot be, then there's no way. And I would say that banks would have to use more than just facial recognition if there's twins involved. Okay, you probably want to pair it with what handphone he's carrying. Maybe there's also, you can also make the assumption that his handphone is, he didn't give his handphone to his twin to, pretend it's not there. But even if he does give his handphone to his twin, so what? It is with his consent. So there are all these ways around. But I can say definitely that it's all a function of the training of if you cannot see the difference, then odds are the algorithm cannot tell the difference either.
Yeah, maybe I just
Sure,
can
sure, sure.
clarify a bit lah. If you are using a passport, the passport identify you. So the facial recognition will get all the facial data, see whether how close it matches you. So maybe it matches you 99%, 98%, or 97 if you accept, then okay. If you are very stringent, then 95 also you don't accept. Then this person cannot come in. So they already know who you are. If you are using a phone, then your phone will have a ID. So you scan, maybe a phone display a QR code, you scan to say who you are. Or your phone has a Bluetooth, and then you go near, it detect you. Then the thing will identify you. You cannot just use a face on the roadside and then you identify this fella. They are too close. Even a photograph also, they are inside. And then, so you cannot just, as what Poseng asked, you cannot just use the face alone. You must use the IC, fingerprint, or you tell them who you are. You tell the bank who you are. Then the bank will use the face to verify who you actually are. Now, like that. Oh, so answer Poseng or not?
Yeah, I think you answered it very well. But I was told that if you take a photograph, they are able to detect that it is fake, you know. Somehow they need the real face because of 3D effect, you know.
No, not Facebook can, because if somebody take a photograph and then upload to Facebook, Facebook will inform all these people whose faces are inside that photograph. Even you happen to be a stranger standing next to the group, it will also inform you that, hey, you are in this group. Because you are a Facebook user. If you are not a Facebook user, they won't know who you are. Because you are a Facebook user, you already log in. So they know your GPS location. They know you are there. And this photo is also in the same area. So they can confirm that. Otherwise, it's very difficult. No? Because you look at the percentage, it's only 0 to 100. And there are 6 billion people in this world. How to get?
So in a nutshell, the face is not like a fingerprint. Okay, it can recognize people to a very high degree, but it is not unique in the sense that, you know, nobody else in the world has the same fingerprint that you have.
Daniel, I have one
Yes.
question.
Sure.
Assuming that the system is trained, using a full face of a person, and then what happens if the same person puts on mask and sunglasses? Will the system be able to identify this person?
In a nutshell, not really. I'm dealing with a couple of issues because what you all just mentioned, wearing masks, another one is what we call liveness detection. It's actually some things that have already been considered or are in the process of being considered in face recognition technology. Okay, is somewhere on this slide too, just a bit further on. Okay, so if you allow me to proceed, I shall get there.
Thanks.
Okay. Okay, the last one, and the reason why I put it is it's interesting because it tells you exactly what a feature is. The DLIP facial landmark detector. The DLIP, which I said is one of the libraries which is closed OpenCV, has this actually scans the face and uses a convolutional neural network to detect 68 points. And these are the 68 points it tries to develop from the tip of the ear, right ear, to the tip of the left ear, 17. to the tip of the nose. So after it has these numbers of your face, I think the numbers is stored is the what now? Is the magnitude as well as the direction of that particular point. After it's detected these numbers, it stores that into a vector. So from that vector, you can see that it basically has a measurement of your entire face. Okay, and this is one of the original means where people tried to use face detector. And remember, in the 18th or 19th century, they have those big calipers that they put around people's head. This is basically it, but in a digital sense. Okay, so this is the third feature extracted to describe the face. Okay, now summarily, what did I hear? Okay, the last part of it is face recognition. And as I said, you have the query vector as well as a reference image database from which you are supposed to find the closest matching to the query image here. Okay, so now the face recognition process is you must figure out some way to determine which is the closest match. Now this obviously depends on a few factors. For example, how fast you want to do it, how big is your database, etc., etc. Okay, so some algorithms are some ways that you can say that the query vector is closer to this other vector is by actually figuring out the distance. And the distance itself, there are several distances. I only named 4 of them here. But you can understanding the study of what constitutes distance in a vector in a matrix space is quite complicated. You have L1, L2, cosine, and Hamming. Or you can say that where in the vector space is which reference point is the query image point closest to, and that can be determined by considering, for example, SVC. SVC is faster than this because calculating the distance basically means you need to calculate the difference between the query vector and every single reference image. So if you got 10,000, that is 10,000 every query image, which is kind of taxing on the computer. Another way is vector space. This is a bit faster because it actually tells you where tells you how close to which space you are. Okay, and the last way is to actually have trees. Trees is you can very quickly figure out which is the closest reference vector to the query vector. So these are all just different ways of matching the query image with which particular image in the reference database. And that is the process of face recognition. And that's the last point in face recognition. Okay. Okay, now we have it. There are a few issues about face recognition that must be discussed about, to have a better understanding of it. But before I carry on, are there any questions of how the algorithm is implemented? No, Okay, there are 4 issues which I can think of. Okay, there are probably a lot more than this, but I can think of 4. Okay, the first one, and definitely the biggest problem, is training. Now, training is a process of actually developing this database of features. Now, like for example, training takes input reference data and converts it to a form that allows for answering queries. Okay. Issues with training. If you train the reference database based on Amorphous, then what's going to happen? So when you try to recognize Chinese face or African faces, then it's a bit less accurate. I wouldn't say it's totally inaccurate, but it's less accurate. So it's so inaccurate that that somehow or other, oh dear, hang on. Here it comes. Somehow or other, excuse me, the US government study confirms most face recognition systems are racist. Okay, why is it racist? If you train your database and it so happens that you have more black people than white people in a particular database of prisoners, then of course, the next time a black face comes out, it's more probable that that black face will be classified as a criminal. Okay, so this also applies to men and women also. If you train everything on men, then it's harder to recognize women simply because that there is less women in the database. Okay. Incoming voice call. Is anybody trying to call me? Stop really. Okay. So, hello? Hello? Okay, sorry. So you can see, training the database is very difficult to do. Somebody is calling me. Sorry, hello? Hello? Okay, I don't know what. So you can see, it's quite difficult to do. So to have a fair database, you need to to recognize people fairly across all races and all sexes, etc. You actually need a more fair training database. We'll go on. Okay. And there is a problem. Sorry, something is buzzing. I'm not sure what it is. Okay. And also, when you train, it's not simply to put 1 or 2 or 3 or 4 images. Ideally, there should be 20 to 30 images for training one face. Okay. And of course, the solution is to, I can think of a solution now, but basically you cannot escape 20 to 30 images. It's just how do you extract the 20 to 30 images only. Okay, so that alone, these two alone, you can see that the quality of the algorithm is very, very dependent on the training. Okay. Now issue a breath mask. The recent solution now, there are 2 ways. Either you have your face with a breath mask, or you can actually simulate a breath mask on an existing photo. Simulate just basically means you put a rectangle over or something like that. And then you simulate the breath mask and then you train from there. It works. It's not perfect, but it works. Because you have to understand that the full face is used to express, goes into a vector. Just like remember you saw this, like this part here. The whole face is used to express the feature vector. So if you cover half of this, that means the training is only on this part alone. So that it may work, but it won't be as accurate because usually the more features you can train on, the better. But it will work. if you go to that that website that I previously showed you, the Pi image search, there are already tutorials available on how to do with a breath mask. Okay, light conditions. I've got a light on, but if I don't have a light staring me in the face, my picture will be something like that. So a lot of cameras actually have a problem with darkness. They just don't show as much light. So obviously the way to read this is to actually pre-process this picture and so that all the features get done. You're not going to be able to get much features from here because everything is evenly black. Okay. Now there are a few ways you can do it. It's generally called low light image enhancement. You can either play the gamma adjustment, do something called a log transformation algorithm, what is recommended as what is called image inversion, which basically you invert the whole image, but when you invert that means from black you change to white and white you change to black, something like that. And then you remove the haze because that will automatically result in a lot of haze. So you remove the haze from that. And there are several other more complicated algorithms, but there exist algorithms that can actually they can actually improve the lighting conditions. So low light image is also another problem. And finally, liveness detection. Okay. Okay, there are many ways around liveness detection. I've not done all of them. You see, texture analysis, frequency analysis, variable focusing analysis. Okay, I've done this. Check the picture for eye movement, lid movement, and blink detection. That means once you have recognized the face, you wait, your program actually wait for one of these things to happen. And if all three happen, even better. Okay, but the problem with this is that, yeah, it does take processing time while you're waiting for the blink to happen, or the lid to happen, or the eye move to happen. Another way is optical flow algorithm to actually check out the 3D face of shape or a combination of all these. So you can do enough algorithms here to make sure that they don't put a photo in order to make sure. I mean, if they, on the other hand, put actually a live photo, that means through the handphone or what, then maybe something texture analysis or frequency analysis will be able, or this first three will be able to tell with different types of tell between having the face on a smartphone. See, this also is in that Pi image search website. So if you really want to go into this, this is a wonderful place to start. How do I get that? Okay. Any questions on these issues? Because after this, I'll just be going to applications away from the technical aspects of it. And
maybe another few minutes, they need to go toilet break again.
Again? Okay, so I need to come, we'll need to come back again.
Minutes. No, you got anybody want to ask him question?
Okay, then I come back again.
Come back again. You're going to think what ask. Then go toilet, then come back again and ask question. Okay, bye-bye. No, bye-bye, come back.